Good afternoon, everybody. Today, I'm going to introduce an exotic kernel called Transkernel, bridging monolithic kernel to peripheral cores. This is a joint work between Shuang, Zhai, Qiao, and my advisor, Felix from Purdue ECE. One sentence summary, what is Transkernel? It is a novel OS model that runs unmodified monolithic kernel binary on the microcontroller-like core of a heterogeneous SOC. It features a novel combination of two key techniques, dynamic binary translation and kernel service emulation. To motivate this work a little, we first introduce ephemeral tasks in smart things. And here, we refer those smart things to be smart watches, smart speakers, and other IoT devices. Ephemeral tasks, they are prevalent among these smart things. They include push notifications, periodic sensor data logging, etc. To execute such an ephemeral task, the kernel has to go through a phase called device suspend resume, where the kernel wakes up all your I/O devices, for example, graphics controller, your MMC controller, and then it can execute the task. After that, it will put all the I/O devices back to sleep, that is, suspend. However, these ephemeral tasks are energy hungry, shown by prior study. They consume 30% or even more higher energy in these smart things. We find that device suspend resume is the key bottleneck. Why is device suspend resume so inefficient? The first reason is that the I/O devices takes time to do power state transition. As a result, the CPU is kept waiting. And the second reason is that the complex device dependencies prevents the process from further optimization. Hence, such a procedure mismatches CPU. And our proposal is to run suspend resume on the peripheral core. What is a peripheral core, you may wonder? Just look at the die photo. You may easily notice that large areas are occupied by CPU and GPU. However, there's this little guy shown here is our peripheral core we're talking about. It is a microcontroller core, and it's much wimpier. However, it delivers lower idle power and with higher busy execution energy. On this heterogeneous SOC, our CPU and our peripheral core, they are asymmetric processors. They share heterogeneous, however, similar ISAs. The ISAs from the same family, however, with different profiles. Also, the CPU and the peripheral core, they are loosely coupled. They can be turned on and off independently. They share the platform resources, including IRQs and DRAM. We find that many SOCs fit our hardware model. Back in 2010, we have OMAP 4460, which is equipped with peripheral core M3 plus the CPU A9. And at present time, we have Azure Sphere, which is Microsoft's IoT reference platform, equipped with the peripheral core M4 and the CPU A7. So here's the problem. Now we have a heterogeneous SoC, which has the CPU and the peripheral core. We're running a commodity monolithic kernel, Linux, for our own sin. And we want to offload the device suspend resume to the peripheral core because we want to keep the CPU asleep as much as possible, resulting in the following workflow where the device suspend resume is purely running on the peripheral core and the user task is still executed by the CPU. So what are the approaches? One may want to use a multi-kernel, right? You can write both kernels from scratch, main kernel and the peripheral kernel, where the peripheral kernel only runs device suspend resume code. These two kernels communicate through a message passing fashion without sharing any states. However, you lose compatibility with Linux. Look how sad the penguin is. And also, it's not easy for you to reuse the Linux kernel driver, which is diverse and mature. The other approach is you code transplant the existing device suspend resume code from the Linux kernel and static compile it to run on the peripheral core. These two kernels share the same single instance of kernel state. However, this also has a problem because the suspend resume code is not self-contained at all. Instead, they depend on a complex stack of kernel software, including driver kernel, driver library code, and a kernel library code. And these codes are stacked on the interfaces, which is known to be unstable. The third approach is a little bit crazy, which is you run a full virtual execution on the peripheral core. Simple, you can implement the lightweight virtual executor on the peripheral core, for example, a DBT. Because the peripheral core lacks hardware support for virtualization, you are facing a 25x overhead if you just port that QEMU, for example, the DBT to the peripheral core and run it. And one should also consider that the peripheral core is much more wimpier than the CPU and runs on a slower clock speed, so that this results no energy benefit at all. Instead, our approach, called Transkernel, the goal is to offload the inefficient device suspend resume code of Linux kernel, run it on the peripheral core, however, with an affordable overhead and thus achieving energy efficiency. The approach is that the peripheral core dynamically translates the kernel binary and executes it. However, underneath, it's supported by a small set of emulated kernel services. By emulated kernel services, we mean a small set of functional equivalent services that's required on the code suspend resume code path. We will explain these services later. Let's put transkernel in the OS design space. Compared to multi-kernels, Barrelfish, M3, where you write kernels from scratch, you lose compatibility with Linux kernel. However, we have compatibility with Linux kernel, compared with K2 Popcorn, which span a monolithic kernel, 2 heterogeneous cores. We actually don't have to reason about the interface problem. And compared with the DBT, for example, Qmu, we have a much more lower overhead. Transkernel follows the following 4 principles. First, translate stateful code, emulate stateless code. By stateful code, we mean the offloaded code that must share states with the kernel, and the stateless code does not. And for example, we translate the kmalloc function because we want to maintain a single instance between the CPU and the peripheral core. However, we choose to emulate the scheduling services. Thus, the peripheral core has its own copy of a scheduler, which does not share state with the kernel, with the main kernel. The second principle is to identify a narrow translation emulation interfaces. This is the interface where the translated code makes down call to the emulated code, requesting kernel services, for example, scheduler services and the spin locks. By doing this, we make the maintenance of those emulated services much easier because you don't have to change your emulated services every time when kernel changes. The third principle is to specialize for hot paths. We observe that for 99% of the execution, device suspend resume follows a common beaten path, which it sees no error and it will get all the resources it requested. These are the hot paths that we talk about, and we specialize for them. In case we go off the hot path, we can migrate back to the CPU to continue execution. And this simplifies our DBT implementation and also make the engineering efforts tractable. The fourth principle is to exploit the isosimilarity between the CPU and the peripheral core. And here, the isosimilarity means the same set of general purpose registers, the identical usage of control flow register, as well as the conditional flag semantics. This reduces the emitted instructions for DBT, and it is key to the low overhead. We introduce ARC, an ARM-based transkernel implementation on platform OMAP 4460, equipped with the peripheral core M3 plus the CPU A9. Here is the full software stack you can see running on the peripheral core, where the Linux kernel is taken in and translated by our cross-ISA from V7A to V7M DBT. And within the box are the full kernel services that will be translated. They are stateful because we want to maintain the single instance with the kernel. They include driver-specific code, driver library, kernel library, IRQ handler, and deferred work, which is the bottom half of the IRQ handler. Underneath are the emulated kernel services we provide. They communicate with the translated code through this stable interface. These emulated services only have small number, 12 functions plus 1 variables. ARC reports the QMU to the peripheral core to implement the cross-ISA DBT. And we're able to derive the translation rule from the formal specification. We found that out of 558 ARM v7a instructions, there exist 447 that can be directly translated to a single v7m instruction, which is shown in this green part. For others, in the orange and red part, we have to emit additional 1 to 4 instructions to emulate. And our DBT engine is able to correctly execute over 200 million instructions through our benchmark. We verify this that by dynamically comparing the execution results with the native kernel and also statically examining its kernel's translated code. So in evaluation, we want to answer, does ARC incur low overhead? does Arc incur tractable engineering efforts? And does Arc actually yield any energy benefits? And we'll run the benchmark as follows. We use a user space test script to run the whole spin resume path, which will invoke 9 diverse drivers. And we record the execution time, cycle counts of the CPU and the peripheral core, as well as the energy. Let's first look at the DBT overhead. From the figure, we separate the suspend and resume DBT overhead. The x-axis stands for the diverse benchmark drivers that we use in the benchmark, and the y-axis stands for the overhead, where the overhead is the ratio, cycle count ratio between the peripheral core and the CPU. As we can see, without any optimization, where is the baseline QMU, it exhibits up to 25x overhead. However, with Arc's low overhead DBT, we are able to bridge that gap to a 2.7x across the benchmarks. We show that Arc reuses Linux with low efforts. With 10K implementation, which is one-time efforts, we are able to transparently reuse 40K lines of kernel driver code in our evaluation only, and conceptually, more drivers can also be reused. We show that Arc maintains good compatibility with multiple versions and configurations of Linux. We support from version 3.16 and up to kernel version 4.20. So the Linux penguin is happy now. Let's look at the end-to-end execution time and the actual energy benefits. Let's look at the execution time first. From the top to bottom, we run the native execution, which is the spin resume on the CPU only, and the Arc, and then baseline QMU. As you can see, indeed, Arc prolonged the execution time. This is because we run the DBT, has its own overhead, and that the peripheral core runs much slower than the CPU. Let's look at the energy. In fact, Arc indeed saves energy, resulting in a 34% of energy saving. Where does this energy come from, you may wonder? This is because Arc runs on the peripheral core, which has much lower busy execution energy, as well as a negligible idle power, as you can see in the orange part and the green part, which is completely shortened or removed in the Arc's energy consumption. However, there is one thing interesting in our experimentation, is that Arc incurs higher DRAM energy. And we conclude that is because the peripheral core only has a small size of last level cache, which is 32 kilobyte. And the thrashing of the small last level cache causes the high DRAM traffic, which ultimately results in the high energy. We conduct a what-if analysis because the energy saving is majorly impacted by 2 factors, the DBT overhead, which is the x-axis you see, and the kernel execution behavior, which is the percent of time spent in the native execution, in the busy execution, which is the y-axis. And the red zone is the part that we actually waste energy, and the green zone is the part we can save the energy. Without any optimization, a simple baseline straightforward port of the DBT can actually waste 3x more energy than the native execution. However, with our DBT optimization and Arc, we're able to push all the way to the green zone, ultimately resulting in a 34% of energy saving. This is only made possible by our low overhead DBT. So to conclude, some takeaway messages. Arc and Transkernel is a novel OS model. It features 2 key techniques, dynamic binary translation and identifying appropriate translation versus emulation boundary in a monolithic kernel. To operating system, we contributed a new model to span a monolithic kernel across heterogeneous cores. To DBT, we show that while the cross-ISA DBT is under the assumption of efficiency loss, it can enable efficiency gain, even on the off-the-shelf hardware. And also, we show that DBT can be applied to translate a specific path of a very complex software stack. To architects, we advocate a heterogeneous SOC design that is friendly to Transkernel. We advocate the equal rights for the peripheral core, which shares IRQ DRAM with the CPU and has the right size of last level cache. And that concludes my talk. I would like to take any questions.
Nice work. I have a couple of questions. So You exploit the ISA similarity, as you mentioned on the slides. How does it work on a truly heterogeneous core? Say, for example, ARM plus, say, a RISC-V.
That is a very good question. So the ISA similarity we exploit here is based on the assumption that they are actually from the same ISA family, however with different profile. That is the assumption that we think made by the architect. So they choose to implement the different profile that has simpler semantics so that they can have energy saving. In terms of cross ISA, really like cross family, like from x86 to ARM, that will have presumably higher overhead. And we have a discussion in translating ARM v7a to v8 to v7 in the paper. So you can check it out to see how ARC can apply in this scenario.
All right. Thank you. One more question. So you said like if there's a failure case, you hand it off back to the CPU, right? So I'm not sure if I missed it. So do you turn off the main core before handing off?
Yes.
So if there is a handoff back again, so you wake up the CPU core, right?
Yeah.
So do you measure in this corner case, like how much energy, do you consume more energy in this case or less energy in total?
That is a great question. So the workflow of work works like this. First, the CPU, the kernel, main kernel, will shut all but one CPU. Then it handles control over to our peripheral core. Then it shuts down the last CPU. Then ARC will finish all the system resume work. And in case of emergency, it will fall back to the main CPU by sending an IPI. And then also, we'll also migrate the stack running on the peripheral core back to the kernel stack on the main kernel to continue execution. So the implementation detail is also in the paper. And we do not measure the energy, but we indeed measure the time to wake up the CPU. It takes around 20 microseconds, so it's pretty fast.
All right, thank you.
Let's thank the speaker again.